the natural exponential function. Let's talk about a special number that we call the natural base, and that is the number abbreviated as e. E comes from the following process. Suppose we have the expression 1 plus 1 divided by n, quantity raised to the n power. And now let's suppose you plug in increasing values of n into this formula. So for example, when n equals 1, we have 1 plus 1 divided by 1, which is 2, raised to the first power, which is 2. If you plug in 5, you have 1 plus 1 divided by 5, which is 1.2, to the fifth power, and that would give you 2.48832. Now what's interesting about this expression is if you continue to increase the value of n, you don't get an ever-increasing value in this expression. In fact, what you'll notice is that the values here seem to be getting close to some number. Well, the number that this is getting close to is the number that we define to be e. And the first several decimal places of e you can see here, but in essence, we usually say e is approximately 2.72. So what I'm telling you here is that the expression 1 plus 1 divided by n, quantity to the n power, approaches this number e, which is approximately 2.71828, etc. And this happens as n increases without bound. So we say as n approaches infinity. Turns out this number is extraordinarily special. In fact, this is one of the most important numbers in all of mathematics, and it leads to perhaps the most important function in all of mathematics. And this is the natural exponential function. So the natural exponential function is simply the function f of x equals e to the power x, where e is the number we just previously defined. Now let's recall that e is a number in between 2 and 3. So if you graph y equals 2 to the power x and y equals 3 to the power x, it should come as no surprise that y equals e to the x would be an exponential function that is right in between these two functions. And so it has all the same behavior as 2 to the x and 3 to the x. But the base itself is extraordinarily special, and we'll learn more about why it's special in calculus. The first thing we need to be able to do is evaluate expressions involving this number e. So for example, if I want to raise e to the third power, this is very simple to do on a calculator, but every calculator is a little bit different, and you'll need to figure out where that e button is on your calculator. Typically, what you will see is a button on your calculator that is labeled LN, and the e button is normally right above it. And so to use it, you have to use an inverse key or a second key on your calculator. But again, every calculator is different, and so your calculator may not display this function in this way. So once you have your calculator handy, go ahead and practice plugging in these values. So e cubed is approximately 20.086. 2 times e to the negative 0.53 power is approximately 1.177, and e to the 4.8 power is approximately 121.510. Just make sure that you can get these values on your calculator. So here we want to sketch the graph of each of the following functions. First, we want to graph e to the power negative x, and then 3 times e to the 0.5x. And you can see I have the graphs here already on the screen. Now, graphing e to the negative x isn't too bad. We know that y equals e to the x is this function, right? It has this shape. And if we know that e to the negative 1 is the same as 1 over e, then we can write e to the negative x as e to the negative 1 to the power x, and that would be 1 over e, quantity to the power x. And we learned in a previous video that if you have the graph of some exponential function with some base, The graph of the exponential function with the reciprocal base is going to be a mirror image across the y-axis. So that's one way we could graph e to the negative x. Now, of course, another way to graph e to the negative x would be to literally just plug in values of x into a calculator and find y values for this, and then just plot those points. But in this case, you actually can get the graph of e to the negative x without using a calculator. Now, for the function 3 times e to the 0.5x, you could perhaps sketch a graph of this without a calculator, but in this case, because the graph is being vertically stretched and at the same time horizontally stretched, it's better just to plug in some values on a calculator. So here I have 7 values of x. If you plug in those values, you should get these y values, and then you can simply plot those points. But what I want you to notice is that this graph still looks like an exponential function, right? Okay. The natural exponential function can often be used to model certain types of things in the natural world. For example, the exponential model for the spread of a virus. So here in this example, let's suppose an infectious disease begins to spread in a small city of population 10,000. After T days, the number of people who have succumbed to the virus is modeled by the following function. Now, this is a complicated function, but notice that there is an exponential function component to this function. So in part A, how many infected people are there initially at time equals 0? So for this, we just have to let t equal 0, and in this case, we're going to get v of 0 is equal to 10,000 divided by 5 plus 1,245 times e to the negative 0.97 times 0. Now, negative 0.97 times 0 is 0, and e to the power 0 is 1. So this is just 5 plus 1245 times 1. And that's 5 plus 1245, which is 1250. So we have 10,000 divided by 1,250. And if you divide this on a calculator, we have 8. So at the beginning, we have 8 people who have this virus. For the next part, we want to find the number of infected people after 1 day, 2 days, and 5 days. So now we're just going to let t equal 1, t equal 2, and t equal 5. And when we do this, we get v of 1 equals 10,000 times 5 plus 1245, e to the negative 0.97 times 1. And then we're just going to plug in t equals 2 and t equals 5. And I'll go ahead and show you how to plug in the first one here. And the important thing here is when you type this into a calculator, when you hit divided by, you need to put parentheses around the denominator here. But this first value, if you round to the nearest whole number, because we are talking about people, this would be 21 people. And the next two values are 54 and 678. And so what you can see is that the number of people catching this virus is increasing rapidly. Now for the last part, it says graph the function v and describe its behavior. So we'll go ahead and bring in a picture of that graph. And what you can see is that in the beginning, very few people have the disease. After a few days, more and more people get the disease. So for example, after 5 days, 5 days is right about here, you can see the number of people that have the disease appears to be some number at approximately 600 or 700, and that is the 678 there. And more people catch the disease here, but then it begins to level off. And so after 10 days or so, there will have been approximately 2,000 people who have caught the disease. So not all 10,000 people in the town are going to get the disease. And this is because of various factors, one of which would be that some people are simply immune to the disease. But this is a sort of logistic style of function. And you can see it has some exponential properties of increasing numbers getting the disease at first. but then it does level off. And this is a much more realistic model of how things work in the real world, because in the real world, things can't increase to infinity. And of course, another common example for the natural exponential function is continuously compounded interest. So I want to remind you of the formula that we used before for compound interest. And this formula is valid for putting a principal P into the bank at an interest rate R for T years and compounding it N times per year. If something is continuously compounded, there is no more N in the formula, because basically what's happening here is N is going to infinity. So the interest is being compounded every minute, every second, every split second. It's being compounded all the time. So it's compounding an infinite number of times per year. And it turns out that when you do this, you get a new and simplified formula. A equals P times E to the R times T power. As an example, we'll do the same numbers that we did before, 3 years, investing $1,000 at an interest rate of 12% per year, but this time compounded continuously. So let's go ahead and plug this into our formula. The amount of money we should have will be 1,000 multiplied by E to the power R, which is 12%, which is 0.12, multiplied by 3. And then we're just going to type this into a calculator. Now, the value that we get here is approximately $1,433.33. Now, I do want to bring in the results from the previous video where we did these same exact numbers, but we did it for compounding once per year, twice per year, 4 times per year, etc. And I want to compare the results. Now, what I want you to notice is that there's very little difference, especially between compounding daily, which gave us $1,433.24, and compounding continuously. And we had mentioned before that there's not much difference really between all of these values. In other words, if you were putting money in the bank, does it really matter if they compound quarterly versus daily? I mean, you do earn approximately $7 or $8 more, but is that going to be a big deal over 3 years? I mean, the answer to that is no, right? So actually the number of compoundings per year doesn't matter that much. Even compounding continuously is not that much of an advantage. Now, it does produce more money, but it's not the biggest factor. So as I mentioned before, and I want to mention this again, the most important thing to consider when putting money in the bank is the interest rate. It's not the number of times that they compound it per year. Changing the interest rate is going to have the largest effect on the amount of money that you would receive. And that concludes this video lesson.